Hi everyone, my name is Claire Tomlin. I'm a professor of electrical engineering and computer sciences at Berkeley. And this is the 17th module in a series that we're recording to support the class EE221A, Linear System Theory at Berkeley. In this module, we're going to introduce a linear time-varying system. So we're going to introduce the notation that we use and discuss it in the context of dynamical systems that we've been introducing over the past couple of modules. So we typically define a linear time-varying system in terms of a matrix notation. So we use the following notation. Typically we use R. So R is the system representation. We use this sort of function notation indicating a function of time, that it's time varying. And we define it in terms of four matrices, A, B, C, and D. Okay, so in this module, we're going to talk about what this means, so in terms of this model itself, what it means, why the model satisfies a Lipschitz condition. We'll talk about its linearity, and we'll set up the framework for thinking about solutions to that differential equation, which we'll treat in the next module. Okay, so what does this notation mean? Well, it refers to a differential equation and an output equation by which we can then further define the dynamical system. Okay, so this stands for the following. The following representation, and this is typically what people would call the state space representation of a system. So we've been dealing with states when we talk about dynamical systems. So the A and B matrices come into the differential equation describing the system evolution. And the C and D matrices come into the output equation, or the readout map. Now, we're thinking about the dimensions of the state and the input and the output in a way that complies with our dynamical systems theory. So typically, X is a vector in Rn. And remember, just to be precise, let's keep it X is a function over time. So X at a particular point in time is a vector in Rn. U at a particular point in time is a vector in Rni. And Y is a vector in Rn out. Okay, so that's the dimensions that we're looking at. So then the dimensions of the corresponding matrices, A is an n by n time-varying matrix. Okay, so what that means is it's a matrix whose entries themselves are time-varying. So the coefficients of that matrix can depend on time. B is an n by ni dimensional matrix. So n because x dot is dimension n, and u and ni because u is of dimension ni. C is an n out by n dimensional matrix, and D is an n out by ni dimensional matrix. Okay, so that's really what we mean by that notation. We also have associated to that differential equation and output or readout map, we have an initial condition. So x at time t0 is equal to x0, where t0 represents our initial time. Typically, we're looking at, as I said, at vectors that are in Rn, Rni, Rn out. So typically, these matrices have real entries. They could be functions of time, but the entries are real numbers. So A of t is a matrix whose entries are real numbers. Okay, so we have the input and the output at a particular time belong in these spaces. And then we also remember our notation, an input function over time. So it's a function which takes time and gives you an input value which is in this space, and similarly output functions over time. So in terms of thinking of this as a dynamical system, we have an input function space, an output function space, where that defines the set of functions that are allowable inputs and outputs. We have a state space, which in this case is Rn. We have a state transition function, and that remains to be computed. So here, as we talked about previously, this is a differential equation which describes the evolution of the state, but it doesn't give you exactly what you need for a state transition function. A state transition function gives you the value of the state at a particular time, given that you started at an initial time with an initial state, and you know what the input is over that time interval of interest. So the state transition function still has to be computed, but this equation here gives us the readout map. It gives us the value of y at time t, given that we have a value of x at time t and u at time t. And the equation itself through c and d could depend on time. Okay, so this is precisely the readout map of the system. Okay, so now let's take a look at that differential equation. We also have built up a machinery for analyzing solutions to differential equations, or when, given a differential equation, does there exist a unique solution? Okay, and that's interesting because, as we said before, looking at that differential equation, in order to get at the state transition function, we would need to be able to solve that differential equation. So does there exist a unique solution to that differential equation? Well, let's check. So let's look at that differential equation and ask, does it satisfy a Lipschitz condition in x? So is it Lipschitz continuous in x? And is it piecewise continuous in time? Okay, well, let's approach the piecewise continuity in time first. The only functions that depend on time in the right-hand side of that differential equation are a of t and b of t. So if a and b are both piecewise continuous functions of time, they're matrices, but if they're piecewise continuous matrix functions of time, or alternately you could think of all of the entries of those matrices if they're time varying, if those entries are piecewise continuous scalar functions of time, then the right-hand side of that differential equation will be, and as long as the input is a piecewise continuous function of time, then the right-hand side of that differential equation will be a piecewise continuous function of time. Okay, so if we defined, for example, p of x, so we'll make the right-hand side of that differential equation, we'll call it p. T. Let's define that to be a of t, x of t, plus b of t, u at t. So if we have, so x is to be determined. If a, b, and u are piecewise continuous functions of time, then p itself is a piecewise continuous function of time. So let's include that in our definition. Let's make sure that a, b, and u are piecewise continuous in time. Okay, so they're functions of time. So they're piecewise continuous functions. All right, so that's fine. Now let's look at Lipschitz continuity. Let's look at this function p and ask whether or not it's Lipschitz continuous in the state x. And so if we try to derive a Lipschitz inequality on p, so let's look at p of x1 of t minus p of x2 of t. And let's look at that. So for a fixed u, when we take that difference, the term that depends on u cancels, and what we end up with is that's equal to a of t times, or a of t times, let's keep this inside the brackets for now, x1 minus x2, and then that's just the norm. So I've taken the norm of both sides. But now I can look at that norm, and I can break that down using my understanding of induced norms. So the induced norm on a matrix A, induced from the vector norm on x and p, that's less than or equal to the induced norm on A times x1 minus x2, the norm difference of that. Okay, so the piecewise continuous function that's a candidate Lipschitz function here is just the induced norm of A of t. And since A of t is a matrix that exists and it's piecewise continuous in time, that's a given, then this term here, the induced norm of A, provides a valid Lipschitz function for this inequality. Therefore, and it's, if it's defined everywhere, it's a global Lipschitz function. Thus, this term here gives us our Lipschitz function, and it allows us to say that differential equations with that right-hand side are automatically Lipschitz continuous in X if A of t exists and is piecewise continuous. This induced norm, again, it could be any of the induced norms you want to use. It's induced by the vector norm that you use over here. So I just called it I for induced norm. But if I were using the 1 norm here, that would be the 1 norm, the induced 1 norm, the 2 norm. All the vector norms we discussed are equivalent. So it doesn't matter which norm I use, but whatever norm I choose, this becomes the induced norm from that particular vector norm. Okay, so what we've defined is a system in terms of a matrix differential equation and a readout map. We've shown that differential equation and initial condition. And we've shown that that differential equation is piecewise continuous in time, is Lipschitz continuous in X. So there exists a unique solution to that differential equation. We'd like to try to understand what that solution is so that we can compute it, and we can then assess things like the linearity of this system. So in order to assess the linearity, we have to look at the response of the system. And to look at the response, we need to understand what the state transition function is, because that would have to be plugged in here for the value of x of t in order to get the full response. So we need to be able to compute the solution x of t to that differential equation, given that initial condition, plug it in here, and then assess whether or not that is a linear system. So we're claiming by stating at the top that this is a linear system, but we still have to show it according to our definition of linear dynamical systems. I can tell you right now that it's not a time invariant system. I can tell you, because we said that as the title, it's a linear time varying system. But you can see it in the definition of the system, that the matrices which define the system depend on time. So the system definition could change drastically from some initial time at time 0 to some later time 100 seconds later or 2 hours later. The A's and the B's and the C's and the D's, those could have changed. We're allowing them to change. So then it's clear that, or it should be clear, that the solution to that differential equation depends on when you start. Just because the matrices defining the equation themselves change, or they could change depending on time. So it's time varying, it's not necessarily time invariant, and it's linear, yet we still have to show that it's linear. Okay, so in the next module, we're going to approach trying to understand what the solution to that differential equation is given that initial condition. Thanks very much.